Hello everyone, welcome back. I'm Madam Sheila and today we'll be learning about operating system services. Okay, so this is an outline of what we're going to be learning today. So the objectives that we're going to achieve from this chapter are to identify services provided by an operating system, to illustrate how system calls are used to provide operating system services, to compare and contrast monolithic, layered, microkernel, modular, and hybrid strategies for designing operating systems, to illustrate the process for booting an operating system, to apply tools for monitoring operating system performance, and design and implement kernel modules for interacting with a Linux kernel. Operating systems provide an environment for execution of programs and services to programs and users. One set of operating system services provides functions that are helpful to the user. User interface. Almost all operating systems have a user interface, and it varies between command line, graphics user interface, touch screen, batch. Program execution. The system must be able to load a program into memory and to run that program and execution either normally or abnormally. Input-output operations. A running program may require input-output, which may involve a file or an input-output device. Lastly, the file system manipulation. The file system is of particular interest. Programs need to read and write files and directories, create and delete them, search them, list file information, permission management. Okay, continue. Communications. Processes may exchange information on the same computer or between computers over a network. Communications may be via shared memory or through message passing, packets moved by the operating system. Error detection. Operating system needs to be constantly aware of possible errors. It may occur in the CPU and memory hardware, in input-output devices, in user program. For each type of error, operating system should take the appropriate action to ensure correct and consistent computing. Debugging facilities can greatly enhance the users' and programmers' abilities to efficiently use the system. Another set of operating system functions exists for ensuring the efficient operation of the system itself via resource sharing. Resource allocation. When multiple users or multiple jobs running concurrently, resources must be allocated to each of them. There are many types of resources like CPU cycles, main memory, file storage, input-output devices. Logging. To keep track of which users use how much and what kinds of computer resources. Protection and security. The owners of information stored in a multi-user or networked computer system may want to control use of that information. Concurrent processes should not interfere with each other. Protection involves ensuring that all access to system resources is controlled. Security of the system from outsiders requires user authentication, extends to defending external input-output devices from invalid access attempts. This is a view of operating system services. Command line interpreter. Command line allows direct command entry, sometimes implemented in kernel, sometimes by systems program. Sometimes multiple flavors are implemented and are called shells. It primarily fetches a command from user and executes it. Sometimes commands built in, sometimes just names of programs. If it's the latter, adding new features doesn't require shell modification. This is what Bourne Shell Command Interpreter looks like. Graphical user interface. User-friendly desktop metaphor interface. It usually has mouse, board, and monitor, and the icons represent files, programs, actions, etc. It has various mouse buttons over objects in the interface, cause various actions to provide information, options, execute function, open directory known as folder. And it is invented at Xerox PARC. Many systems now include both command line and graphical user interfaces. Microsoft Windows is graphical user interface with command line command shell. Apple Mac OS X is Aqua graphical user interface with Unix kernel underneath and shells available. Unix and Linux have command line with optional GUI interfaces. Touch screen interfaces. Touch screen devices require new interfaces. Mouse is not possible or not desired. Actions and selection are based on gestures, and virtual keyboard is for text entry. It also has voice commands. This is the Mac OS X GUI. System calls. Programming interface to the services provided by the operating system. It's typically written in a high-level language like C or C++, and it's mostly accessed by programs via a high-level application programming interface rather than direct system call use. And there are three most common APIs, which are Win32 API for Windows, POSIX API for POSIX-based systems, including virtually all versions of Unix, Linux, and Mac OS X, and Java API for the Java Virtual Machine. Note that the system call names used throughout this text are generic. Example of system calls. System call sequence to copy the contents of one file to another file, from source file to destination file. This is an example of standard API, and I believe that you can read it on your own. System call implementation. Typically, a number is associated with each system call. System call interface maintains a table indexed according to these numbers. The system call interface invokes the intended system call in operating system kernel and returns status of the system call and any return values. The caller needs to know nothing about how the system call is implemented. They just need to obey API and understand what operating system will do as a result call. And most details of operating system interface hidden from programmer by API, and it's managed by runtime support library, a set of functions built into libraries included with compiler. For this one, I will explain in class later. System call parameter passing. Often, more information is required than simply identity of desired system call. Exact type and amount of information vary according to operating system and call. There are three general methods used to pass parameters to the operating system. The simplest is to pass the parameters in registers, and in some cases, there may be more parameters than registers. Parameters stored in a block or table in memory and address of block passed as a parameter in a register. This approach taken by Linux and Solaris. Parameters placed or pushed onto the stack by the program and popped off the stack by the operating system. Block and stack methods do not limit the number or length of parameters being passed. Okay, so for this diagram, I will also be explaining about it in class later. Okay, moving on to the types of system calls. We have process control. It is to create process or terminate process, to end, abort, to load, execute, to get process attributes, set process attributes, and wait for time, wait event, signal event, allocate and free memory, dump memory if there's error, and is a debugger for determining bugs, single step execution. And it logs for managing access to shared data between processes. Second, we have file management. It is to create file, delete file, open and close file, read, write, reposition, get and set file attributes. And the third one is device management. It is to request device, release device, to read, write, reposition, to get device attributes, set device attributes, and logically attach or detach devices. The fourth one is information maintenance. To get time or date, set time or date. To get system data or set system data. And to get inset process, file or device attributes. The fifth one is communications. To create, delete communication connection. To send, receive messages if message passing model, to host name or process name, from client to server. Shared memory model, create and gain access to memory regions. To transfer status information and to attach and detach remote devices. And the last type of system call is protection. To control access to resources, to get and set permissions, to allow and deny user access. This is an example of Windows and Unix system calls. This is standard C library example. C program invoking printf library call, which calls write system call. This is an example of Arduino. It is single tasking and there is no operating system. The program Sketch is loaded via USB into flash memory and it has single memory space. And the bootloader loads program, and when the program exits, the shell is reloaded. For FreeBSD, we have Unix variant and it's multitasking. When user login, it invokes user's choice of shell, and shell executes fork system call to create the process, executes exec to load program into process, and the shell waits for process to terminate or continues with user commands. Process will exit with code equal to 0, which means there's no error, but if the code is more than 0, it means there's an error code. System services. System programs provide a convenient environment for program development and execution. They can be divided into file manipulation, status information sometimes stored in a file, programming language support, programming loading and execution, communications, background services, and application programs. And most users' view of the operating system is defined by system programs, not the actual system calls. Also, it provides a convenient environment for program development and execution. Some of them are simply user interfaces to system calls, others are considerably more complex. For file management, it is to create, delete, copy, rename, print, dump, list, and generally manipulate files and directories. Status information. Some ask the system for info like date, time, amount of available memory, disk space, number of users. Others provide detailed performance, logging, and debugging information. Typically, these programs format and print the output to the terminal or other output devices. Some systems implement a registry, which is used to store and retrieve configuration information. Next, we have file modification. Text editors to create and modify files, special commands to search contents of files or perform transformations of the text, programming language support. Compilers, assemblers, debuggers, and interpreters sometimes provided. Program loading and execution. Absolute loaders, relocatable loaders, linkage editors, and overlay loaders, debugging systems for higher level and machine language. And for communications, it is to provide the mechanism for creating virtual connections among processes, users, and computer systems. It is also to allow users to send messages to one another's screens, browse web pages, send electronic mail messages, log in remotely, transfer files from one machine to another. Then we have background services. It launches at boot time. Some for system startup, then terminate. Some from system boot to shutdown. It provides facilities like disk checking, process scheduling, error logging, printing, and it runs in user context, not kernel context. It is known as services, subsystems, daemons. And then we have application programs. They don't pertain to a system, and it is run by users. It is not typically considered part of operating system, and it is launched by command line, mouse click, finger poke. Linkers and loaders. Source code compiled into object files are designed to be loaded into any physical memory location, like in a relocatable object file. Linker combines these into a single binary executable file. It also brings in libraries, and the program resides on secondary storage as binary executable. It must be brought into memory by loader to be executed. The relocation assigns final addresses to program parts and adjusts code and data in program to match those addresses. The modern general-purpose systems do not link libraries into executables. Rather, dynamically linked libraries, in Windows it's called DLLs, are loaded as needed, shared by all that use the same version of the same library, and it's only loaded once. Object executable files have standard formats, so operating system knows how to load and start them. This is the role of the linker and loader. The reasons why applications are operating system specific. Apps compiled on one system are usually not executable on other operating systems. Each operating system provides its own unique system calls, like they have their own file formats, etc. Applications can be multi-operating system. It is written in interpreted language like Python, Ruby, and interpreter available on multiple operating systems. App written in language that includes a VM containing the running app like Java, and it uses standard language like C, and it compiles separately on each operating system to run on each. Application binary interface is architecture equivalent of API, defines how different components of binary code can interface for a given operating system on a given architecture, CPU, etc. Design and implementation of operating system is not solvable, but some approaches have proven successful. The internal structure of different operating systems can vary widely. Start the design by defining goals and specifications. and is affected by choice of hardware type of system. User goals and system goals. User goals. Operating system should be convenient to use, easy to learn, reliable, safe, and fast. System goals. Operating system should be easy to design, implement, and maintain, as well as flexible, reliable, error-free, and efficient. Specifying and designing an operating system is a highly creative task of software engineering. Policy and mechanism. Policy. What is there that needs to be done? For example, interrupt after every 100 seconds. Mechanism. How to do something. For example, timer. Important principle. Separate policy from mechanism. The separation of policy from mechanism is a very important principle. It allows maximum flexibility if policy decisions are to be changed later. For example, change 100 to 200. Implementation. There's much variation to it, like for early operating systems in assembly languages. Previously, we had system programming languages like ALGOL and PL1, and now we have C and C++, and actually there's usually a mix of languages. It has the lowest levels in assembly and the main body in C, the systems programs in C, C++, scripting languages like Perl, Python, and shell scripts, and there's more high-level language that is easier to port to other hardware but is much slower. And emulation can allow an operating system to run on non-native hardware. Operating system structure. The general purpose operating system is a very large program, and there are various ways to structure ones. For a simple structure, we have MS-DOS, and more complex one like Unix, and layered one we have an abstraction, and for microkernel we have Mach. For monolithic structure, we have original Unix, and Unix is limited by hardware functionality. The original Unix operating system had limited structuring. The Unix operating system consists of two separable parts, system programs and the kernel, which consists of everything below the system call interface and above the physical hardware. And it provides the file system, CPU scheduling, memory management, and other operating system functions, which is a large number of functions for one level. So this is the traditional Unix system structure. It is beyond simple but not fully layered. The original Unix operating system used a simple layered approach, but almost all the operating system was in one big layer, not really breaking the operating system down into layered subsystems. Next, Linux system structure. Here we can see the monolithic plus modular design. Another approach is to break the operating system into a number of smaller layers, each of which rests on the layer below it and relies solely on the services provided by the next lower layer. And this is called the layered approach. The operating system is divided into a number of layers according to levels, each built on top of lower layers. The bottom layer, layer O, is the hardware. The highest layer, layer N, is the user interface. With modularity, layers are selected such that each uses functions, operations, and services of only lower level layers. This approach allows each layer to be developed and debugged independently, with the assumption that all lower layers have already been debugged and are trusted to deliver proper services. The problem is deciding what order in which to place the layers, as no layer can call upon the services of any higher layer. and so many chicken and egg situations may arise. Layered approaches can also be less efficient, as a request for service from a higher level has to filter through all lower layers before it reaches the hardware, possibly with significant processing at each step. Microkernels. It moves as much from the kernel into user space. Mach is an example of microkernel, and Mac OS X kernel, Darwin, partly based on Mach. Communication takes place between user modules using message passing, and the benefits are easier to extend a microkernel, easier to port the operating system to new architectures, and is more reliable, less code is running in kernel mode, and is more secure. The detriments is performance overhead of user space to kernel space communication. This is the microkernel system structure. Modules. Many modern operating systems implement loadable kernel modules. It uses object-oriented approach, and each core component is separate. Each talks to the others over known interfaces. Each is loadable as needed within the kernel, and overall, it is similar to layers but with more flexible, like Linux, Solaris, and etc. Hybrid systems. Most modern operating systems are not one pure model. Hybrid combines multiple approaches to address performance, security, usability needs. Linux and Solaris kernels in kernel address space, so monolithic, plus modular for dynamic loading of functionality. Windows mostly is monolithic, plus microkernel for different subsystem personalities. Apple Mac OS X hybrid layered Aqua user interface plus Cocoa programming environment. Below is kernel consisting of Mach microkernel and BSD Unix parts, plus input-output kit and dynamically loadable modules called kernel extensions. This is Mac OS and iOS structure. This is Darwin operating system. For Android architecture, it is developed by Open Handset Alliance, mostly Google, and it's open source. It has similar stack to iOS, and it's based on Linux kernel but modified. It provides process, memory, device driver management, and it adds power management. The runtime environment includes core set of libraries and Dalvik virtual machine. The apps are developed in Java plus Android API. Java class files compiled to Java bytecode, then translated to executable, then runs in Dalvik virtual machine. Libraries include frameworks for web browser like WebKit and database SQLite, multimedia, and smaller. As you can see here, this is the Android architecture. Building and booting an operating system. Operating systems generally are designed to run on a class of systems with a variety of peripherals. Commonly, operating system has already installed on purchased computer, but can build and install some other operating systems. If generating an operating system from scratch, write the operating system source code, configure the operating system for the system on which it will run, and compile the operating system, install the operating system, and boot the computer and its new operating system. Building and booting Linux. Download Linux source code from this website here and configure kernel via make menu config and compile the kernel using make, produces VM Linux, the kernel image, compile kernel modules via make modules, install kernel modules into VM Linux via make modules install new kernel on the system via make install. System boot. When power initialized on system, execution starts at a fixed memory location. Operating system must be made available to hardware so hardware can start it. Small piece of code like bootstrap loader, BIOS or BIOS stored in ROM or EPROM locates the kernel, loads it into memory and starts it. Sometimes two-step process where boot block at fixed location loaded by ROM code, which loads bootstrap loader from disk. Modern systems replace BIOS with Unified Extensible Firmware Interface. Common bootstrap loader GRUB allows selection of kernel from multiple disks, versions, kernel options. Kernel loads and system is then running. Bootloaders frequently allow various boot states such as single user mode. Operating system debugging. Debugging is finding and fixing errors or bugs. Also performance tuning. Operating system log files containing error information, and failure of an application can generate core dump file capturing memory of the process. Operating system failure can generate crash dump file containing kernel memory. It is beyond crashes. Performance tuning can optimize system performance, sometimes using trace listings of activities recorded for analysis. Profiling is periodic sampling of instruction pointer to look for statistical trends. Debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it. Performance tuning. It improves performance by removing bottlenecks. Operating system must provide means of computing and displaying measures of system behavior. For example, top program or Windows Task Manager. Tracing. It collects data for a specific event, such as steps involved in a system call invocation. The tools include strace, which is to trace system calls invoked by process, GDB, source level debugger, perf, a collection of Linux performance tools, and TCP dump, which collects network packets. BCC, also known as BPF compiler collection, debugging interactions between user level and kernel code nearly impossible without toolset that understands both and an instrument their actions. BCC is a rich toolkit providing tracing features for Linux. For example, disksnoop.py traces disk input-output activity, and many other tools in the next slide. Yay! So that was the end of chapter 2, and thank you for staying till the end. I'll see you on the next chapter. Bye!